In this video, I'm going to talk a bit about the polarity of molecules. So some molecules are called polar molecules, and this is because they have an uneven distribution of electrons between the atoms. And the behavior of polar molecules is different than nonpolar molecules. And we'll actually see that a little bit more in the next video. And the polarity of molecules is based on the differences in electronegativity of the atoms within a molecule and on the molecular structure of the molecule. So remember, electronegativity is one of our periodic trends, where it's going to increase as we go from left to right, and it's going to increase as we go from bottom to top. And so the fluorine is actually going to be the most electronegative atom on the periodic table. And people have actually come up with ways of putting numbers to these, and so you can look at the differences in electronegativity. So for instance, a non-polar bond is when the electronegativity difference between the atoms involved in the bond is less than 0.5. And a polar bond is when the electronegativity difference between atoms involved in a bond is greater than or equal to 0.5 but less than 1.7. If we end up having greater than 1.7, then the difference is so great that one of the atoms actually just takes the electron from the other one, and so we end up with an ionic bond. And so that tells us that a bond can be polar, but what about the polarity of a molecule? So we can look at two different molecules here. We have methane on the left and formaldehyde on the right. And so we can look at the electronegativity numbers for each of the atoms in these. And so we see that with the methane, we have 2.5 for the carbon and 2.1 for each hydrogen, 2.5 for the carbon and 2.1 for the hydrogen on formaldehyde, but then 3.5 for the oxygen on formaldehyde. And so we have these small dipoles for the bonds here in the methane that go that way, and then two that go that way. But we see that these ones cancel each other out, so those ones don't matter. These ones also cancel each other out, so those ones don't matter. But then with the formaldehyde, we have these two and then this one. These two cancel each other out, so those don't matter. And we're just left with the dipole between the carbon and oxygen. And so that means that the methane there on the left has no net dipole moment. And then the formaldehyde on the right does have a net dipole moment, and so that would actually be a polar molecule. We of course saw in the previous video that we can have three-dimensional structures for these, and that actually becomes important for determining the polarity of a molecule as well. So let's look at something like this. So with the methane, the dipoles of each bond were actually pretty small, but we can have something like carbon tetrafluoride, where we have these dipoles between the carbon and fluorine that's actually 1.5. So the electronegativity difference is 1.5. That means that each of these bonds themselves is polar. But does that mean that the molecule itself is polar? So we'll take a look at this and see how we can determine that. So what we want to do is actually put these arrows end to end and see if we end up back where we started. So if they end up back where we started, then we have a non-polar molecule. If we get somewhere different, then we have a polar molecule. So if you've taken any kind of physics, you would know that this is just vector addition. And so we can put one of the arrows here. We can put the next one starting at the tip of the other one going that way, then this one going that way, and then this one going that way. And it looks like we just end up right back where we started, so there was no net change here, and that means that there is no net dipole in this molecule. So even though each bond is polar, we saw earlier that they have 1.5 difference in the electronegativity. Because they all cancel each other out, there is no net dipole in this molecule. And now if we look at something like water, where we see that there is dipoles oriented this way, and there is a difference in electronegativity of 1.4, so these bonds are polar, but we want to know if the molecule itself is polar. And so again, we do the same exercise. We put these end to end like this. So we end up at a different point than we started at. So there is this much difference between them. That is our net change there. And so that means that we have a polar molecule. There is a net dipole here. And so that means that the molecule is polar in this case. So let's take a look at a few examples here. And I would encourage you to pause the video and try each of these on your own and see if you can come up with the Lewis structure, then the 3D structure, and then determine whether the molecule is polar or not. So for the first one, we have this ammonia, so that would have a 3D structure that looks like this. We have these dipole moments. If we put them end to end, we would have something that looks like this. We see there is a net change, and therefore there is a net dipole. And so the ammonia is a polar molecule. Now, if we look at the sulfur trioxide, we want to put our dipoles for each bond that look like this. We put them end to end, we would end up with something that looks like this. And so there is no net change. That means this molecule has no dipole moment. It has no net dipole. It is a non-polar molecule. We'll try this with our sulfur dioxide. We again put our dipole moments on the bonds here. If we put them end to end like this, we see that there is a net change now, and therefore there is a net dipole. That means that this would be a polar molecule. If we try this with this methanol here, what we would see is that for the hydrogen to carbon, those would be small enough. The carbon has a 2.5, the hydrogen's 2.1, so it's only a 0.4 difference. That means they're small enough that we would just call those non-polar bonds. But we do have these polar bonds here between the carbon and oxygen, between the hydrogen and oxygen. And if we put those end to end like this, we see that we get a net change. Therefore, there is a net dipole on it. That would make the methanol a polar molecule. Now, if we look at the hexane here, we want to determine whether this is going to be a polar molecule. So recall that with the methane, these all cancel out. If we put these end-to-end over here, we see that we end up right back where we started, no matter where we start from. And so this would be non-polar. Then if we add another carbon onto this, we see that we still end up with all of these canceling out. If we add yet another carbon, they all cancel out. Another carbon, they still all cancel out. And another carbon, they still all cancel out. And so you can kind of see where this is going. No matter how many carbon and hydrogen bonds we put onto here, we will end up with something that is non-polar. They will always all cancel each other out. And so anything that is just a hydrocarbon, like the hexane here, is going to be non-polar. But what about if there is a long hydrocarbon chain with just a single polar OH bond on it? So that means we have this long hydrocarbon chain here, then just this OH on the end. Where remember we saw earlier with the methanol that the OH does have a polarity to it. But when we're looking at something like this where we have a very long hydrocarbon chain, the rule of thumb is that if there is more than 4 carbons in the chain, then the molecule becomes mostly non-polar, and so it will actually behave like it has no net dipole. Even though we have this dipole over on one end, there is just so much non-polar character on this molecule that it behaves as if it is non-polar. And so a few things to keep in mind from all this. The quintessential polar molecule is water. This gives it a lot of the important properties. That is why it is so important for life here on Earth. And so whenever you hear water, just think that that is a polar molecule. The quintessential non-polar molecules are any of the hydrocarbons, like the one we looked at. So these are molecules that contain only carbons and hydrogens, such as the hexane that we looked at before, the C6H14. And polarity determines many of the physical properties of substances. These include things like the melting point, the boiling point, the solubility in different solvents. So for instance, polarity is why water and vegetable oil don't mix. That's because water is polar, vegetable oil is non-polar, and so these things will not mix, which we'll talk a bit more about in the next video. And so, like I said, we're going to talk a bit about the consequences of this in the next video. But anyway, that was everything I wanted to talk about in this one. I hope you found this helpful, and I will see you in the next one.